Hi everyone, welcome to part 2 of our lecture on Thermochemistry, chapter 6. Today we are going to talk all about heat transfer and about specific heat capacity. So to start off, we're going to talk about some units of energy. So the first of these is the joule, and that's the amount of energy needed to move a 1 kilogram mass a distance of 1 meter. So that's more of a physics, definition. We'll use it more in terms of heat transfer in this class. It's directly related to the calorie, which is the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. And so we can actually relate these two different values with this conversion factor here. So we have 1 calorie is equal to 4.184 joules. And this is going to be exact, so it's not going to play into our significant figure calculations. So you might be familiar with calories from food, right? If you go to the grocery store and you're looking, to watch your weight, you might look at how many calories are in something. But these food calories are actually capital C calories. And the reason that this is different is capital C calories are actually kilocalories. And so a kilocalorie, right? One big capital C calorie is equal to 1,000 little c calories, which is the same as a kilocalorie, or 4,184 joules. So if you think about like a 100 calorie snack pack, so this is actually a capital C calorie, even though sometimes they'll write it with a lower c, which means that it's really 100,000 calories. But I'm not sure that you would eat something that said it was 100,000 calories, right? So we use these capital C calories in food. So they're slightly different. But in chemistry, we are typically going to use joules. That's going to be our unit of energy. But if you had something in calories, whether that's a little c or a capital C, we can convert that to joules and then use it in our calculations. You may have heard kilowatt hours. That's another unit of energy. We can also relate that to joules because, like I said, in chemistry, we are typically going to use joules or we will use kilojoules for our calculations. So specific heat capacity is something that is different for different materials, and it's how much energy essentially it takes to change the temperature of a substance. So if we look, let's go back a slide. If we look at the calorie is the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. Okay, and so this is actually directly related to the specific heat. Now we're going to use this same kind of theory, but it's going to be 1 gram of anything by 1 degree Celsius. Okay, so the specific heat is going to be the amount of heat required to change the temperature of 1 gram of a substance by 1 degree Celsius. So this will be different for different substances. You'll become really familiar with the one for water. It's going to be 4.184 joules per gram degree Celsius, and this is always going to be our unit, joules per gram degree Celsius. And you'll notice that this number maybe looks familiar from the previous slide because 1 calorie is equal to 4.184 joules. So like I said, that calorie definition, that was the amount of heat it takes to raise 1 gram of water 1 degree Celsius. So if we use this in joules, then it's 4.184 joules per gram degree Celsius. So it's how much energy in joules it takes to raise 1 gram of water by 1 degree Celsius. Okay, so this is the same as 1 calorie per gram degree Celsius. Okay, but we're going to use it in joules per gram degree Celsius. So it's different for different substances. This is the one for water. In general, though, the specific heat tells you how hard something is to heat up or cool down. If it has a larger number, that means it can absorb more heat before it changes temperature. And if something has, a very low, a low number, right, a low specific heat capacity, then it will change temperature very quickly. It can, absorb a lot of heat, can change temperature rapidly. So my example that I like to use is if we think about a pot of boiling water on the stove, or just a pot of water, and we are trying to heat it up. And so, if you're going to think about which thing gets hotter first, right? Is it the metal pot or is it the water inside? Well, the metal pot gets a lot hotter a lot faster than the water does. And you may think, well, duh, it's because this is touching the fire, right? If you have a gas stove, the metal pot is the thing that's actually on the fire and the water is inside the pot. But that's not really why it is. The metal pot has a very low specific heat capacity, maybe around 0.5, depending on what your pot is made out of. And water has a much higher specific heat capacity at 4. 4 is actually a very large specific heat. I know it doesn't sound very big, but it is. So your specific heat of water may be up to 10 times larger than your specific heat of your pot, which means it's going to take 10 times the amount of energy to heat up your water. So that's why that metal pot will get hot much faster than your water does, because the water has a very large specific heat. It needs to absorb a lot of energy before it changes temperature. So here are the specific heats of different substances. Like I said, it's going to be in joules per gram degree Celsius. That's our unit. And as you can see, these metals here, right, that we have, they have very low specific heats, especially compared to water, which I told you is 4.18. Water has a very high specific heat, takes a lot of energy to change that temperature, and it will also stay hot a long time because it takes a lot of time for it to lose all of that heat. Whereas metals with a very low specific heat can heat up very quickly, but they can't retain it. And so they will also cool down very quickly. You'll see it written as C subscript S, but in this class we're typically just going to use it as C because we're not going to use other versions of C. Our units are joules per gram degree Celsius for the specific heat capacity, and then sometimes you'll be asked for the molar heat capacity, and it's more or less the same thing. Now we're trying to figure out how much heat is required per mole to raise the substance 1 degree Celsius. So you may see this as joules per mole degrees Celsius. And so the only difference here is that instead of using grams, now we have moles. So if it's a molar heat capacity, sub out your grams for moles. So here is our equation that we're going to use. This is our specific heat equation. So Q equals mc delta T, or like a lot of us will call it Q equals MCAT, right? Because that delta kind of looks like an A. The Q is the heat lost or gained, and this will be in joules. Our M is our mass of the sample. This will always need to be in grams. Our C is our specific heat capacity. Again, that's going to be in joules per gram degree Celsius. And then our delta T is going to be our temperature change. And when we do our temperature change, this needs to be in degrees Celsius, but it's always going to be the final temperature minus the initial temperature. And this order of events really matters in this class because we need to know the sign of Q. Like we were talking about in the last lecture, right? If Q is negative, then heat is being released. And if Q is positive, then heat is being absorbed. So it's very important that you do this T final minus T initial so that your sign of Q comes out correctly. So let's get some practice. This says, calculate the amount of heat released when 7.40 grams of water cools from 49 to 29 degrees Celsius. And then we have our specific heat here. This is a Q equals mc delta T problem because it's asking for heat, and we have a mass, we have our specific heat, and we have two temperatures, so we can calculate our change in temperature. I do want to tell you, you do not need to go around memorizing any specific heats. It is likely that you will memorize the one for water because you're going to use it so frequently. But you don't have to, and you don't have to memorize any of the other ones. Those will always be provided to you. You do need to know how to solve the problems though. So Q equals mc delta T. So we're trying to find Q. We have our mass is 7.40 grams. Our C value is 4.18 joules per gram degree Celsius. And our delta T, right, so we're doing final minus initial, so it goes from 49 to 29. So 29 is our final temperature. And 49 was our initial temperature. So we get negative 20 as a negative 20 point there for our significant figures as our change in temperature. So then we can go Q equals mc delta T. So we have 7.40 grams. We have C is 4.184 joules per gram degree Celsius. And then our delta T is at negative 20 degrees Celsius. So if we go ahead and math that out, we will get negative 619, but that's got the wrong number of significant figures because we really need to have two significant figures because of this number here. So I'm going to put this in scientific notation. Oh, no, I don't need to, sorry. 620 joules. So now we have two significant figures. And again, make sure that sign is negative because you see water is cooling. And so when water cools, it's releasing heat, right? So our Q should be negative because heat is being lost during this process. Okay, so an application of specific heat is calorimetry. And calorimetry is used to look at heat transfer between two substances. And we know that, in a given set of conditions, right? System and the surroundings. Energy cannot be lost. It can be transferred, but it always must be accounted for, right? Law of conservation of energy. And so the heat lost by one thing will always be gained by something else. So this is kind of the core foundation of calorimetry. And so we can calculate the amount of heat absorbed or released during a physical chemical change, and we can measure it. And typically the way that we measure it will be by the change in temperature. And we can, if we do this reaction in water, we can measure how much the temperature of the water changes in a calorimeter, and then we can use that to calculate how much heat was being absorbed or released during the reaction. Okay, so here is an example of a bomb calorimeter. And so a bomb calorimeter we're actually going to talk more about next time. But a bomb calorimeter is used to burn something, and this actually does not have water, but we'll burn something and then see how much the temperature of the bomb changes, okay, of this calorimeter. The other type of calorimeter that we have is a coffee cup calorimeter, which is what this definition is talking about. And a lot of times the way that we will do this is we'll do a reaction in the water. And the reaction usually is exothermic, and so the reaction will release heat. And when it releases heat, it causes the water to heat up, right? Because all of the heat released by your reaction will be absorbed by the water. So if the water absorbs that heat, it will increase in temperature, and we can measure that using the thermometer. Okay, and so we can use this, how much the temperature of the water changes to figure out how much energy was released from the reaction. Okay, so this is called a coffee cup calorimeter, and I know that doesn't sound very fancy for us, but it actually works really, really well. We'll typically use, as you can see, there's two coffee cups here, and we call these nested coffee cups where we stack them to make sure it's really insulated, and then we put a lid on the top to make sure that no heat is releasing to the atmosphere. So in this way, we can say that all of the energy that's being lost by our reaction is being absorbed by the water. So in this, our reaction would be our system, and the surroundings would be our water. And the bomb calorimeter on the left, like we'll talk about last time, again, this is going to be completely insulated, and so we've got, energy will be released by whatever we're burning, and it will be absorbed by the calorimeter, and we can measure how much that temperature changes to figure out how much energy was being released by, say, the food that we burned. Okay, so two different types. Today we're going to cover the coffee cup calorimeter. So, like I said, we're going to do a reaction in our water. It's probably an aqueous reaction. Maybe it's a double displacement or precipitation reaction. And we're going to measure how much the temperature of the water changes. That's the key. So we're looking for the change in temperature to tell us how much energy is being released or absorbed by our reaction. Okay, so when we place two different objects together, and a heat is able to flow between them. And remember, heat is always going to flow from something that's hot, right, from the thing at higher temperature to the material at a lower temperature. And it will continue to flow until they reach the same final temperature. And this is really important for calorimetry because the reaction will continue to change, right? Say the reaction is continuing to release heat, the water is continuing to absorb heat, and it will keep doing that, right? That water will keep absorbing heat until they reach the same final temperature. So you might want to make yourself a note when we're doing calorimetry that TF is going to be the same for both sides of your reaction. And like I said, this is going to be a closed system. So all of the heat that's being lost by one thing is going to be gained by another. So we can set this as the negative Q hot, right? Because all of the energy being released by the hot thing, right? That's why we have it negative. All of the energy being released by whatever's hot is going to be absorbed by whatever is colder. Okay, so if we have our Q's equal, then we can also set our MC delta T's equal because Q is equal to MC delta T. So we'll sub in our MC delta T's. And so we'll get negative MC delta T for all of the hot side is equal to MC delta T of the cold side. And again, we can do these calculations because of the law of conservation of energy. All of the energy being lost by the hot stuff is being gained by the cold stuff. And typically, when we do these type of calculations, our hot thing that we're calculating is usually going to be a metal. We're putting a hot piece of metal into some cold water and then looking at how the temperature changes. Again, not always, but that is one application of this, and you'll see it pretty frequently. So like this. It says a hot piece of metal weighing 350 grams is heated to 100 degrees Celsius. It's then placed into a coffee cup calorimeter containing 163.2 grams of water at 22 degrees Celsius. The water warms and the metal cools until the final temperature is 35.2 degrees Celsius. And again, this is the final temperature for both substances because they're in thermal contact, right? So the energy will keep flowing until they reach the same temperature. And then it says calculate the specific heat of the metal and identify the metal. And we have the specific heat tables there on the right. So we have negative Q of the hot stuff, in this case that's the metal, is going to equal positive Q of the cold stuff, which in this case is the water. So all of the energy that's being lost by the metal as it cools down will be gained by the water as it heats up, right? Again, that's because it's in that coffee cup. So we're saying that no energy goes anywhere else. All of the energy from the metal will be absorbed by the water. So it's important to keep that lid on while you're doing these experiments. So if negative Q of the metal is equal to Q of the water, we can go, okay, negative MC delta T of the metal is equal to MC delta T of the water, okay? And we're solving for the specific heat of the metal. So we have negative, right? We have 350 grams for our metal. We don't know C. And our delta T here, right? We need to do T final minus T initial. So our final temperature for both is 35.2 degrees Celsius. So we'll do 35.2 degrees Celsius minus our initial temperature of our metal was 100 degrees Celsius. So 100.0 degrees Celsius. So that takes care of the metal side. And then we have the water side. So we have 163.2 grams of the water. Our C value for water is 4.184 joules per gram degree Celsius. And then our delta T for the water, again, our final temperature is the same, 35.2 degrees Celsius, and minus the initial temperature of the water, which is 22.4 degrees Celsius. Okay, so now we can go ahead and math all of that out. We will get 22,700 C for this side is equal to, let's see, the other side, 8,740. Okay, and this is both, well, I've kind of removed the units for now because we'll get to, it starts to get to be a mess. As you can see, we've got grams degrees Celsius on this side, and we've got joules over here, just the way that it works out. But again, if I know I'm solving for C, a lot of times I'll leave out the units until the end. If you like to play with units, you go ahead and keep them all around. So then we can go ahead and just divide, and we will get C is equal to 0.385 joules per gram degrees Celsius. And again, keep track of your significant figures as you go. Okay, so once we've got our C value, then we can go ahead and identify our metal. So 0.385, this is copper. Okay, so again, we can do these type of calculations because of the law of conservation of energy. All of the energy being lost by the metal is being absorbed by the water, and they have that same final temperature, so we can do these calculations. Let's try another one, a little bit trickier. In this example, we are going to solve for the final temperature of both substances. This is a little bit tricky because we will end up with TF on both sides. So I wanted to show you one of these types of calculations so that you know how to do it. So again, we have some aluminum, and our aluminum is going to be hot, and we're going to put it in some cold water. Okay, and again, since they're in thermal contact, right, they are touching, one's hot, one's cold, they will end up at the same final temperature. Okay, so again, we're going to say, okay, our negative Q of our metal is going to equal our Q for our water, which means the negative MC delta T of our metal is going to equal MC delta T for our water. So we can go through negative, and we have our metal is 32.5 grams. Our C value, there's our C. Our C value, 0.903 joules per gram degree Celsius for aluminum. And our delta T, we're going to break this down into TF minus our T initial. And so our metal was at 45.8 degrees Celsius. Okay, and then we'll do the same thing for the other side. We have 105.3 grams of water. Our C value for our water is 4.184 joules per gram degree Celsius. And then our delta T, again, we're going to do T final, which we don't know, minus our T initial, which was 15.4 degrees Celsius. And again, as I go through this, I'm going to go ahead and leave out the units, but I know I'm going to end up with degrees Celsius at the end because we're solving for a temperature. If you want to keep all of your units as you go for it. So on the left here, we're going to end up with negative 29.3 times TF minus 45.8 is equal to 440.6 times TF minus 15.4. And then if we go ahead and we distribute things in, we'll get negative 29.3 TF plus 1340 is equal to 440.6 TF minus 6,790. And so then we can go ahead, I'm going to take all of my, just numbers by themselves over to the left and my TFs over to the right, and I will get 8,130 is equal to 469.9 TF, which means we get 17.3 degrees Celsius is equal to TF. Okay, so there you go. So again, I wanted to show this one because this is what happens if you have your TF on both sides, and you'll just need to combine your variables at some point so that you can solve for it. It's just like you might do in algebra if you were solving for, you had an X on both sides that you were trying to solve for. Same kind of thing, except now we have TF. And that's it. That is our lecture on calorimetry and specific heat. So go ahead and get lots of practice on these problems. The next time we are going to talk about bomb calorimetry and see how those calculations are different. But for now, get some practice on this type of calorimetry, do the lecture worksheet problems, and as always, if you have any questions, send them my way. See you guys next time.